Thank you for having me here. My name is Slawomir Goryczka, and on behalf of Michele, we are both software and security engineers at Google. On behalf of Michele, I would like to present you Security Signals. It's a framework to scale web security, which we use extensively at Google. So what I will present today is we'll start with a basic introduction to web security, just to understand a little bit what we are talking about. Then how do we collect the security signals? How do we process them? What do we do with them? And then we will continue with the ways of using security signals. How do we use them? What are the use cases for security signals? And we end up with one of the remediations which we implemented for cross-site request forgeries. And we'll show you how one of the mitigations was rolled out across the whole company there. At the end, we will have time for questions, so please keep them until the end of the presentation. So what is web security? Well, what are the web services? That's maybe the most important question there. So web services are essentially any processes, any services, applications that are implementing HTTP protocol. So we have users which are also talking in HTTP language. They are sending HTTP requests, and a web application or web service is generating HTTP response for that request. So it's pretty obvious that our attack surface are both the web services or any intermediary between our users, clients, and the web services. One of the examples of those intermediaries, they are sometimes called user agents. Those are essentially browsers, which you know very well. So vulnerabilities can be seen both either on the browser side, which is the agent, or on the web application, web service. What is important here when we are talking about the HTTP protocol is that in both HTTP request and response are sending data, but they are also sending metadata. And these metadata are in the form of HTTP headers. So think of them as a key value, maybe not storage, but as a key value pairs. And those HTTP headers are usually pretty good signals, pretty good informations, which are enough to tell us about potential attacks, but also defenses that have been applied by the web service and by the developers. So we will focus on headers as well. It sounds simple. So the question is, why is it so difficult? Well, at Google, the first answer is scale. So we are talking about managing and improving and taking care of the security of more than 8,000 web services. They are evolving all the time. Those services are hosted behind around 1,000 domains, host names, and they are processing roughly trillions of HTTP requests and responses every day. So this number you can keep in mind. We will use it later to do a little bit of the math when it comes to the data. The web services serving those trillions of responses are pretty heterogeneous. So we can see services implemented in Java, C++, Python, Go. They use different HTML templates, different engines, different sanitizers. There are billions of lines of code, thousands of third-party libraries and other dependencies. Some of them we don't have a lot of control, of which we don't have a lot of control. And the most important thing there, all of that is in motion. All this environment is evolving, is changing all the time. New code is added, old code is deleted, new dependencies are introduced, new vulnerabilities, new attacks, new mitigations are needed. So all of that is changing all the time. What can we do here? Well, the obvious answer is let's start fixing vulnerabilities, let's start fixing bugs. But it won't scale. There are not enough security engineers, and well, we would get bored pretty fast with that. So instead of doing that, what we are doing at Google is we are building and maintaining an ecosystem or developers environment, which we want to to make it secure by design, meaning everything which is in part of that environment should be secure, of course, but it should allow you to implement your functionality as a developer and maintain the security kind of no matter how you assemble all the blocks and pieces. Of course, if you want to be unsecure, you can, with a lot of effort, you can still make mistakes, but it should be very difficult and not used very often. That's why we as a security engineers, as a security organization, we need to build this developers' infrastructure, environment, ecosystem, and then keep maintain it at this level. So we need to provide guidelines and recommendations for developers. Please use this framework, please do not use this framework, or the same framework with different version. We need to provide tools, libraries, also predefined solutions, which are very frequent needed for teams who are not experts in security. So like use these set of dependencies, and then everything else will be taken care of for you. So that's one side. On the other side, in many cases, what we see are some exceptional cases, corner cases, special cases, where all what we provide is not enough. So we need to have some custom approach for any exceptions, anything which is not recommended, but still needs to be implemented in that weird way. And when we already have that, when we build this, we need to keep maintaining it. So we need to see if there is any regression. We need to detect it and fix it. The same with the blind spots. If we see that there is anything which we missed, we need to look after it, take care of it. So it's not like one product where you just deliver and you go. You have to keep maintaining this ecosystem all the time. Our approach to do that is to engage in many places, as you will see later, security signals framework. We use it for many different purposes. Some of them are security, but you will also see that there are some non-security related use cases which surprised us a lot. So security signals is a framework which collects both static and usage data related, of course, to security. We call them signals because we needed a name which doesn't tell us much, which is not a vulnerability, which is not an exploit, but at the same time it carries pieces of and bits of information which are very useful when we are talking and looking into security of applications. So with that information, with the signals, we generate some insights. We are able to automatically report bugs, prioritize works, manage those bugs even. And what do we get with that? Well, first of all, we have a visibility. We know what is the security stance of our web infrastructure. It's pretty big, in fact, pretty big achievement. It's not very common in the market. We can optimize resource allocation. So we don't have that many security engineers, and also we don't have that much machines and CPU cycles and other mechanical resources, let's call them that way. So we need to optimize resource allocations. We need to determine if certain applications are secure by design or they've just lost this status because, for example, there is a new attack, new vulnerability discovered today, yesterday, or last week. So for that, we need to also make sure that we have it continuously, and that's what security signals are giving us. Every day we are getting fresh data. Every day we can see if anything has changed. It's not real time because there is no need for that, but with the daily updates, we have a pretty good view into our security stance. So security signals, how is it built? What components do we have there? The framework, the security signals framework, have two main components. One is about collection of the signals. So we have a collection mechanism, which we need to build. We needed to make sure that it's technology agnostic. So no matter what technology, what language, what framework, what web framework are you using, we should be able to get some signals out of it. It has to be also very comprehensive. So because anything which we don't see, any blind spots, are the avenues, are the paths where potential attackers can attack, can look for vulnerabilities and exploit them, and then we won't see them. We won't be able also to make sure that certain mitigations are applied into those blind spots. So we are maintaining this comprehensive collection mechanism for security signals. But then in order to make sure that these signals are useful for us, we need a pipeline. This is the next big component of security signals. It's a batch pipeline in the MapReduce, built as a MapReduce pipeline implemented using Flume Java. That processes lots of data. We'll talk about it in a second. And the results of that pipeline are of course persisted for a short period of time. And then they can be used for alerting, monitoring, automated bug reporting, bug management, and so on. So in the bigger picture, this is the whole architecture of security signals infrastructure. I divided it into three components: collection, processing, and then I will talk also about the usage. All of them are connected, as you can see, through databases, which I will also present. And there is one special arrow, which I hope I can clarify a bit later there. So let's start with the data, with the signals collection. In our architecture diagram, this is the green rectangle. So in order to collect the data, we need to understand how to collect the signals. We need to understand what do we want to collect, where do we want to collect it, essentially how does it work. So oversimplifying the picture first, we have web services, web applications, which are serving HTTP responses for HTTP requests. Well, of course, having a single web application as a single process running on a single machine may work for your family application, but not if you want to serve large amount of provide service for large amount of users on different continents and so on. So we have many instances of the same applications running on many different machines, many different setups and configurations. All of them for users are hidden behind the name of that application. Let's say Gmail, calendar, maps, you name it. So in order to hide this complexity from the user, so they don't need to know the IP of the Gmail server, they just know the name of the service, and then we need something which will route their traffic to an individual instance of the web service running it. So for that, we are using reverse proxy. It proxies application and all the complexity which we have internally from the users. So it's our front end, it's our external front end. And the users, they can also be different. So as users, you can have external users, of course, but you can have also you have also internal users, your employees. They also use your internal network. They will very likely use internal apps, not external ones. Maybe products which are not deployed yet, not in production, like test versions of the product. And you can also have robots, all the scanners, crawlers, anything which is running through internet and looking into pages, and it's not a human being. So what do you do with all those things? Usually you start separating, let's say, based on the user. So your internal network will have internal reverse proxy, and this internal reverse proxy will direct the traffic to internal web applications. But then you need also the reverse proxies, which are faced externally to serve external users and robots. There is one robot there, as you can see there. Reverse proxies have also a little bit more functionality needed, because it's not only enough to know that under this IP I have my application, and under another IP I have different application. They need to also understand how to balance the traffic, so certain nodes, certain machines are not overloaded. They need to have some protections, for example, from denials of service attacks. They need to be able to handle encryption. So terminate the encryption, the HTTPS encryption from the users, and apply encryption which you have internally in your company. And also, it's good if they provide a centralized logging, so you can also start collecting some information about the traffic there. All of that is usually in the packet. You can find some reverse proxies on the market, like Nginx or Envoy. Sometimes companies, they build their own custom reverse proxies. We had that at Google as well. It's called Google Frontend, a bit descriptive name. You may also hear the name GFE, which is an abbreviation of that. And it implements all of that, all these functionalities which I've just mentioned. For us, what will be interesting is the centralized logging. So we want to log signals. But what do we log? How do we do that? How do we make sure that the reverse proxy is not in trouble because of our logging? There are many questions and challenges. I think maybe the even more important is, why reverse proxy? Why do we want to log the reverse proxy? Well, as you can see quickly from the diagram, it's a very nice single point of entrance for the traffic. It also proxied all the complexity of the web applications, so we can just focus on one single point there. One single point of implementation and collect all the information there. But there are lots of challenges there, as you can see. First of all, data size. I mentioned trillions of HTTP request responses every day. We can try to log them. They will not improve our understanding of security that much above the data collected from a sample of the traffic. And that's what we do. For external traffic, we collect up to 1% of the signals from up to 1% of the traffic. For internal, it's a little bit more. It's 10% because the traffic is generated by internal users. We want to also see signals from applications, services which are not enabled for external users. We need a little bit more information there. What is very important is that we do not collect any sensitive data from requests and responses, and we do not store any body of those responses. So just metadata, just HTTP headers, and not all of them, because some of them are carrying information about authorization or cookies, and we don't want them. They are not needed for security. So why collecting them and then having all the trouble of managing that? In the long term, we also don't persist individual HTTP requests and responses, but aggregate the data as soon as possible. They identify them even if needed. But that's not even enough, because there is still a little bit of the risk that maybe there is something which shouldn't be, or something sensitive or risky. That's why we also make sure that the retention of those data is very short. It's short enough, a few days, just to ensure that we can further process them. And even more, the data are highly isolated. So access to them is not possible by human unless you are a member of a security team, and even then you need a justification, and each access is also audited and can be reviewed anytime. So all of that is just to make sure that we have signals. We have some basic information there, but that shouldn't and is not cause any trouble to both the stability and functionality of GFE. GFE still needs to serve its purpose. You shouldn't see any degradation in the performance, no increase in the latency or anything like that. So we need to balance all those, and we are balancing all those setups there, as you can see. So what do we collect? Well, we are starting with the basic information, like HTTP method, get, post, put options, destination host. We need to know where, what host is serving, under what host we are serving the given traffic, redacted path. So path is redacted to remove identification information. We'll talk in details about that in a second. No query parameters, because they may be sensitive. Status code, content type, referrer policy, cache policy, a little bit information about user agent, but only browser name and the main version, because we want to understand what may be the impact, like what is the usage of given browsers, but also how a given response will be interpreted by a browser. So we need to know its version. And a little bit information about cookies, but no cookie value, just security attributes, and usually that's enough. So we need to be very careful what do we collect and aggregate that data as soon as possible. No request response body is collected. That's even a benefit for performance reasons. So we can collect signals, we can sample and collect signals even before the reverse proxy will receive any bytes of the HTTP response body. So it's also beneficial for us. But those basic informations are not enough. We are also collecting signals from security headers, HTTP headers. A lot of them are about policy, content security policy, cross-origin embedder, opener, resource policy, strict transport security policy, and others. I will maybe focus a little bit on the X content type options because it's simple, so it can help us when we will talk about data flow. X content type options is a header in which you can, if you set the value no sniff, you can inform the browser to not sniff, to not try to guess the content type of the body. Even if you specify that the body is HTML, browser may not believe you and try to guess the content. This is the source of lots of problems and vulnerabilities. So we want to make sure that browsers will not do that. We want to make sure that all traffic, for example, has X content type options set to no sniff at the scale of the company. But that's still not enough. It's not enough because we don't know a lot of the information about which are available for web service about the websites. How have they been generated? What checks have been performed? These headers, they don't have that information. So what we did? Well, we introduced our own header. Our own header which carries synthetic security signals. So those are signals which are artificially generated by web applications. They are then transported in the X Google security signals header together with all the other headers in the response, HTTP response. And then our reverse proxy is sampling the traffic, of course. It's collecting the signals, but just after that, it's dropping this header. This header is not leaving Google. It stays, it's blocked by the reverse proxy. Of course, this is not the only X Google header, which are internal headers. There are many others, so we didn't invent it we didn't implement it new pieces of infrastructure there. We just used the existing ones, but it's very, very helpful for us as Google security signals. Yeah, long name. So what do we collect in those synthetic security signals header? An example, a few examples here. So we want to understand what templating system have been used to has been used to generate the website? Was there cross-site request forgery protections? Essentially the token, was it verified by the web application? Was it verified in a way which was approved by and recommended by security team? Was there a presence of any server-side isolation policies to make sure that there is no cross-site attacks on the server side? What web framework was used? What method, function in the code, source code file was used was executed to generate this piece of HTML? It's very useful for when we are talking about remediation and identifying the location in the code where the fix should be added. Also build information. If you are talking about 8,000 services, more than 8,000 web services, with different instances running on different machines, you cannot just update them just in the instant time. It's a process. It takes time, and you want to know if your response was generated by a binary in version X or X+1 or maybe X-1, because there's a problem there. So all these informations, the synthetic security signals, are additionally processed by our framework, and as you can see, they will be very, very useful. But these data, these signals, which are usage signals, are still not enough. We are adding two more groups of signals. One, we call them auxiliary data. We collect them from our internal databases. So informations about teams at Google, code ownership, production environment, source code information, repositories, and things like that. They have a lot with remediations and automated backfiling. But also we have risk signals. So maybe that sounds a bit scary, but those are informations which encode a little bit of our understanding of criticality of a given host name or a given web application. For example, all the domains at Google are split into 5 domain tiers, where domain tier 0, based on the criticality of a given domain. So domain tier 0, in domain tier 0 we have host names, we have domains, which if exploited, if there is a problem there, will have a huge consequences for Google. Anything related to logging, to accounts.google.com would be there. But if the domain is isolated, is sandboxed, for example, then we would put it in the lower domain, maybe even domain tier 4, number 4. So it's very useful if you want to also prioritize your work, but also understand the risk. Like the most risky domains, the most risky web applications are here. We need to focus on them first. That's roughly how they are used. What do we do with those signals? So we collect them, and then we process them. I've already mentioned that we have a pipeline to do that. So let's have a closer look into that pipeline. This is our heart of the security signals framework, where we process those data. The pipeline is Flume Java pipeline. It fetches lots of the data, and it processes them, as I've mentioned. The reason why it has so many functionalities that not everything can be done during the collection time, because, as I mentioned, we cannot cause any performance trouble for GFE. We cannot slow down GFE in its work. So some pieces of the work are moved into the pipeline, as you will see. What this pipeline is doing, it's reading data. Well, I mentioned trillions of HTTP requests and responses are passing our reverse proxies. We sample them up to 1%, so we end up with roughly billions of collected signals every day. So the pipeline needs to reduce that number by doing deduplication, by also reducing cardinality of certain attributes. We'll talk about it in a second. And then the pipeline also joins these signals, these collected signals, with auxiliary data and risk signals. So when you do the join operation, you have to be a bit careful to avoid any data explosion. This is one of the main problem with the pipeline, is to make sure that the output data are not too big. At the same time, the quality of the data is high. And if there are any potential sensitive information, sensitive data, they are redacted and removed. The output of the pipeline is persisted in the security signals table, which has a slightly larger retention time, but not too high. So let's take a look at an example of pipeline's functionality, reduction of the cardinality. So there are I can talk about two attributes which have high cardinality, meaning number of different values which a given attribute can have. So one of them is a user agent. User agent header, you can put whatever you like there. Getting information about the browser and the version, it's harder there. That's why we have user agent hints, which helps us a lot. But in many cases, we found out that we don't need all the super detailed information. It's enough the browser name and the main version of the browser, which we already know. The other problem are URL paths. Often they contain informations which we don't care that much. Or there are sensitive data there, like capability bearing tokens, document IDs, timestamps, user inputs, and they are not that useful from security point of view, and they are a problem from the privacy point of view. So we want to redact them. That's why one of the main functionality of the pipeline is to redact all the URL paths into the path patterns. So how do we do that? We have a 3-step algorithm. The first step, in which we are using our auxiliary data. In this case, we are using information about the API of our web API definition and all the configuration information which we have. It tells us in a given path what components of that path are variable parts, what parts of the path are variable, which one are carrying any identifier, and then we can essentially replace that with a placeholder, Because from the web perspective, you just need one URL which will link to a given URL endpoint, to a given service, and a given action. And that works pretty well. Like 90% of the paths are redacted during the first step. The remaining roughly 10% are then processed by the manually maintained list of well-known high entropy paths. So we need to help ourselves a little bit with manual work. And the last resort is our ML model. It's a small random forest, 11 trees, not that deep not that deep trees, but it works pretty well. So after running this 3-step algorithm, we are pretty sure that our paths or path patterns at this point of time, they are not redundant, and they don't have at all sensitive information. All of that ends up in the security signals table. So in this table, we persist only aggregated and identified data and information. So our pipeline ensures that there are no information about individual requests or responses. Access to that table to these tables is a little bit more relaxed, but it's still, you need to still be approved, and only for certain job roles. It's created every day. It is monitored for the quality of the data. So if suddenly we'll see that there is an anomaly in the number of URL paths of a given service which we detect, we will start investigating what's happening. Was it the product decision? Was there a bug? Was there a misconfiguration? And we retain that data only for 30 days. So the collected signals, just a few days, security signals tables, 30 days. It's enough to perform research, to use them later on. So how do you use these data? How do you use those records? How do you use security signal tables? This is the last part of our architecture, where I will first present you what tools we are using to use the data, and then present a little bit high level use cases, few use cases, high level use cases, and one example using the whole architecture. So 3 main groups of tools which we are using. You can directly look into the table, into all the tables. If you are a security engineer, if you are a security researcher, you want to do some checks, some security checks there. These data are also monitored, looking for example, regressions. Based on that monitoring, we have alerting, automated bug filing, but that's not enough. These bugs are also maintained by us. So if we will see that a certain problem is fixed, or it's not that we cannot detect it anymore, or we can confirm that it's not present anymore, we can close that bug. So we can roughly maintain a reasonable number of open bugs. There is also a very small pipeline, very simple one, which reads that security signal tables and even further aggregate the data for statistics. So we generate aggregated data. It's a pretty small data set, but it gives us information about any trends, statistics, things which will be very useful in the long-term planning or in presenting some informations to individuals. So let's start with the interface for security engineer. So it's our bubble interface, web UI interface. So you can see the data in form of the bubbles. You can click on them, you can expand them. You can also find the missing pieces. It's very useful for researchers, which are focused on identifying, like researchers from the red team, in identifying any gaps. So their goal is to find weak spots, vulnerabilities, try to connect them, build the exploitation path, and then present it to the others so we can fix them. So red team loves that a lot. Monitoring, alerting, and bug filing. When you set it up, it does most of the work for you. It allows us to see the changes over time, and it allows us to fire any alerts if needed, or file a bug. Here, for example, you have an example of one of the rollouts for, I think it's trusted types, where we start with very small coverage, 1% of services of traffic, and then we increase them over time. And you can very nicely see how does it change. Very, very often we don't reach 100% because of those special cases, exceptions, and so on, but we end up pretty high. Those zigzagging, the ones you see there, are caused mostly because we have weekends and the traffic is a bit periodical. So over the weekend it looks slightly different than during the work days. Yes, so usually it looks like that. Then let's assume that you are a product engineer or developer, essentially. You care about security at the company, but even more you care about the security of your product. So you want to have all the security, in this case web security information, in one place, so you can see what is missing, what needs to be done, what is okay. And so you are looking for some kind of security scorecard, one card with all the information which you need about your product. Here you will see, you can recognize that it's about photos. This is a scorecard for one of the action, people action, one of the URL endpoints, for Protos, where you can see that we have information about the code. So we see it's a Java code. We have a button pointing us to a given source code location, also to a build information for a binary that generated this traffic. We have information about the path, about the HTTP method, response code, content type, and at the bottom I just added three of them, but it's a pretty long list. And those are information about collected from the signals. Those are information about mitigations. So let's focus on one of them, content security policy. From this UI, you can see that it's enabled. So we detected content security policy headers. We evaluated them in our pipeline. And we also have additional information, this auxiliary data, from CSP collector. It's a service that collects violation reports, and the reports of the content security policy are sent to that collector, and then we can also expose them in this UI. So it's pretty powerful, and it's used by the teams very, very often. But then, as I mentioned, we also aggregate the data, and this data are very, very useful for senior leadership and executives. They want to see the big picture, but their screens have the same size, so we need to compress the data a bit, and they want to overall understand where are the problems, where is the need to put more work, more security engineers there. They want to understand what is the risk, how risky is launching this application, will it cause any troubles in the future, and all of this information we can provide them here. You have an example of the user interface here, and this information is aggregated together with the level of granularity you are looking for. So we can generate that information for the whole company, for your organization, if you have a small, or your group of products, your product. It's pretty powerful. And I think what is even more interesting here is that all these user interfaces, which I mentioned to you, they use the same data, they use the same metrics. So you can drill down, starting from this dashboard for executives, to individual URL endpoints and understand why certain things are not there or what happened, how to improve them. And then whenever there is a fix, it's immediately it's immediately visible in all UIs for product engineers, developers, for executives, and also for security engineers. So actionability of this is can be presented, and it's very, very powerful to in our daily work. How do we use it at the higher level, let's say? So these use cases with the UI, this is like a daily time and every day how we use it. But at the higher level, what would be our use case? For us, as I mentioned at the beginning, we want to make sure that the developer environment, the environment used by our developers, is safe. So you can write the code, you can implement new product, new functionalities in a safe way, and it's easy. In fact, it should be difficult to do it in the non-safe way. And whatever you design, whatever you build, should be also secure by design. So it should be very difficult or even impossible to build something which is not secure. So we need to provide secure by design frameworks, guidelines, and also features. So that sounds easy if we are talking about new product, because you are just thinking about it, you are designing, you are thinking how to build it. And then you just follow the guidelines, recommendations, you use the security approved frameworks, and you are good to go. But from the moment when you commit the code, when you add the code to the repository, it becomes a legacy code. So you need to also keep maintaining and updating existing code. And you have to do it continuously, because new things are discovered every day, new vulnerabilities, new mitigations are introduced. So it's a constantly ongoing work. You need to also understand this legacy code a little bit, understand where changes are needed, and what is the risk carried by this legacy code. Let's assume that you've already did that. So you identify the problems. You know, okay, this is where we are looking for. Then you have to design mitigations. What do we do with that? How do we improve that? It sounds very simple, like let's just add in one extra header or something. But in fact, again, you cannot interfere with the basic functionality of the web applications. You cannot interfere, let's say, with the Gmail functionality or with the performance of this application. It won't be acceptable. So sometimes these mitigations are deployment or rolling out of this mitigation is a very lengthy process, sometimes even multi-year, and it's sometimes not straightforward. You have to do extra steps. You need to make sure that certain bad things won't happen. You need to verify before you enforce something that, in fact, really it won't cause any trouble. So it's a pretty tedious task as well. Let's see how does it look like usually. So first, we identify services or endpoints which would benefit from that mitigation. Signals are very helpful here because we have a comprehensive view of the web traffic at Google. We can identify those endpoints. Well, okay, traffic is sampled, but if you do a very simple math, you will see that within, let's say, 1 week of data, it's very unlikely to miss something which has just a minimal amount of traffic, just a minimal usage of a service. So it's pretty good there. Then you have to gradually roll out a new service mitigation. 0.1%, 1%, 5%, 10%. After each step, you need to verify that it's in fact that amount of percent. There are no problems with performance. There are no problems with functionality. There is, in fact, a security benefit there. Security signals, the UI part helps here a lot. If there is any problem, of course, you file a bug, you do the rollback. You can do it from our framework as well. That's how you track the progress. All the exceptions, special cases, one of the reasons why you do a gradual rollout is that you don't want to suddenly come to the office and have 5,000 mails because your rollout caused so many problems that people start emailing you. You want to deal them one by one. And if you detect that something is even more serious, you stop the whole process. You think how to solve it at a larger scale. And then if there's any regression, so at the point where you reach pretty high coverage of your mitigation, you want to stop looking into these graphs, these charts, and focus on something else. But at the same time, if something goes wrong, if you start seeing that there is a regression in adoption of the mitigation, you want to get notified. You want to get notified and fix the problem there. A few examples mitigations which have been adopted here are content security policy. This is very nice, not a group of mitigations I would even say, because there is a report-only version of content security policy, which is not enforcing the policy, but just generating any violation reports, which can be collected and analyzed, which we did and do. Trusted types, fetch metadata isolation policies, cross-origin opener policies, and more of them. But there are also additional capabilities and use cases which we observed and were very surprised. So one of them which we which we intended and we implemented, is the JavaScript signals pipeline. Our security signals pipeline didn't have all the information about JavaScript scripts, so we needed something extra. For example, to understand what JavaScript is loaded and sent to the browser. Then we start receiving also emails from web security scanning team. They scan the websites, our websites, pretending to be external users. They have, of course, robots, and they don't do that manually. They test the websites, they interact with the website, and they try to break it in an automatic way. The problem there is that your scanner is as good as your crawler. It's limited by your crawler. If you cannot discover a given URL, you won't visit it, you won't test it. So they came to us and asked, can you give us a few URLs? You are looking into the real traffic. Of course, the raw URLs, we cannot give them. We don't have access to them. Only the pipeline can read them and process them. But those URLs with redacted paths, we just pass them there. And based on these placeholder in those redacted paths, they can replace them with the test data. So for example, if there is information about user ID, then they can take their test user ID and put it in the path. Then they have a full valid URL, and they set their crawlers to go and crawl this URL and then test it as well. Very, very useful. That's why we had this arrow in our architecture diagram. And to our surprise, like 50 teams in the company start using the data. We are constantly discovering new users there for non-security reasons. So they roll out a web feature, or they had a bug, the problem, and they use it to debug their website, the service they are providing. And last but not least, all AI and ML properties, models, they generate some content. This content is used by many different programs, services, but eventually it may be served, or it may be used to serve websites. And thanks to the signals, we know about it. We know those web endpoints which are using AI ML generated content to generate a website. Sometimes it's very obvious if you are using user interface for a given model. Sometimes it's not that obvious. But because of the signals and all of this infrastructure, we are now able to see where do we expose AI models in the web endpoints. What web endpoints are exposing some content generated by them. So it's very, very useful for us. I prepared one example just for the sake of the time, where I would like to go with you through our infrastructure with the data and show you how an example remediation may look like. The example is based on the cross-site request forgery. It's one of the problems which is not that easy to solve properly, at least. So as you all know, any website can fetch resource from any resource from different domain, different location. In the first example, we are including a JPEG, an image of a cat, hopefully, from an example.com domain. Looks pretty good. But so what will happen in the website is that a browser, when we'll see image source, will just send a request, get request to fetch the cat.jpg. But this request can be also interpreted by your web service to perform an action, some kind of action. For example, if you have a router at home and you use the standard setting, your router may interpret this request as a request to turn off the router. It's hidden behind the image, of course, but the image will be broken because no image will be returned. but the request will be sent, and it may turn off your router. Or even worse, you can transfer money without knowing about it. So the last example, we have a form which will send a POST request to mybank.com, sending 10,000, whatever currency you like, from Thomas to Eve, and it will do it automatically because the script at the bottom will submit that form without any interactions when we are just loading the page. Now, why would it work? Why the bank will do something like this? Well, the bank will try to verify who is sending, like what authorization is attached to this request. But let's say if you are logged into mybank.com at the same time when this page is loaded and this form is submitted, your login cookies for mybank.com will be attached to this request because it's the same site, the same domain, and sent to the bank. Bank will see, oh, I see that you are performing this operation as part of our logging session, so I should do that. Why not? Well, as you can see, that's the problem. There are many ways in which you can prevent that from happening. Especially, you can prevent any state changing requests. In this case, the POST. Change of the state is like turning off the router, in this case, transferring the money. And one of the remediation which I want to tell you is to send XSRF token. So in this case, token is generated by the browser together whenever a user navigates on the page. The token is unguessable, so it's random essentially, or should look like random, and be correlated with a client, not necessarily session. So it's difficult to guess, so the attacker cannot guess it and copy it or come up with its value. It's correlated with a client, so attacker cannot pretend, even if that it's related to its session, and the service will be able to verify that it's really request coming from the client because of the checking the token, while checking the token. So it looks easy. Yeah? So we have a token coming to our web services. They need to verify it, and then we are good to go. Yes, if the verification is negative, the response is not served, the action is not performed, the money will not be transferred. If the token is valid, yes, the money will be transferred, the router will be turned off. Well, but then you have to have that implementation in every service, which is at every endpoint, which is a state-changing endpoint. And you won't do it as a security engineer. It will be product developers implementing that, which may not always be done correctly. So if you want to make sure that the tokens are validated by your web application and they are validated in the correct way, you need to first identify all URL endpoints that are implementing this state-changing functionality. So let's say we did that based on the signals, but then how do you know that the validation happened? In security signals, we don't have that information. We don't have that information. We need that information to be passed by the web application somehow. So this somehow are our synthetic security signals. That's why we introduced one of them, CSRF, which carries that information that this we've seen XSRF token, which has been validated, and it's a valid or invalid one. Then, of course, we need to refactor web frameworks that will start populating this signal so we can collect them and learn about the validation. And then, of course, special cases apply, and then we need to repeat that for lower priority domains and services and so on. So it's a pretty lengthy process. Let me just show you one round of it and how it's used based on our implementation, our infrastructure, our architecture. So we start with collecting data about URL endpoints and learning if they are state changing or not. So we do it based on the existing data. Then we implement in, let's say, the first web framework, we implement a piece of code which verifies the XSRF token. And then we tell everybody, please use this piece of code to verify the token. This code will also generate new synthetic security signal saying XSRF token has been verified by this security pre-approved code. And what will happen then? The signal, this synthetic signal, will reach reverse proxy, our GFE. GFE will sample the traffic. The lucky ones or unlucky ones will get collected. But because it's a synthetic signal, it's an ex-Google header, it will be dropped. And the users will not see that header, but we will see it in the collected signals. Then these signals will be processed by our pipeline. In this case, it's relatively simple because it's a synthetic signal, so we know that it's valid. We don't have to evaluate it. We just need to understand its coverage. And then it will end up in the security signals table. So next day, we will be very happy to see the signal in our UI as a security engineers. We will know that our implementation of the synthetic signal in the first web framework is correct. We see the signal, we see the values. So we will repeat the process. We'll take the next web framework, next one. And over time, we will see that our aggregated data will start reporting that there is a higher and higher coverage of our signal. So we will learn more and more about XSRF token validation. What we will detect there, well, probably good and bad things, and good, bad, and ugly. So the good things that there are endpoints, state-changing endpoints, which are using our code to validate the XSRF token, and they are doing it correctly. We know it. We will maintain this code, so no problems there. The bad things is that there are URL endpoints, state-changing URL endpoints, which are not validating XSRF token. And the ugly things that there are URL endpoints that do validate XSRF token, but they are using custom code. This custom code can be even okay, functionally okay, but we don't know how will it behave over time, because the web application, the web service will keep evolving, keep changing, and this code needs to be eventually maintained, and we don't know what will happen. But luckily, based on this information, we can start thinking, what can we change there? Well, the bad things, we can switch to the good ones. So whenever we see that XSRF token validation should be done, we'll just file a bug. Product team will and ask them, please use this piece of the code to validate your XSRF token. We can improve the ugly things. Talking to the team, please don't use the custom implementation, use our library to verify XSRF token. And over time, we should see better and better results. More and more good things, fewer and fewer bad things and ugly things. Eventually, we will saturate. We will see, okay, done. We have some percent of exceptions. Everything else is good thing. We claim it's a success and we can go home. But of course, next day, things may start looking bad again because of the regression, because of the new services being introduced, because code can be changed and so on. So our last action then is to set up monitoring, alerting, and bug filing, automated bug filing, to get notified, to send a bug to a product team and notify them that something is getting worse. For example, your token is not validated for a new URL endpoint, which changes the state. So you need to act based on that. So that was an example where we were able to roll out one remediation for one example of remediation and one part of it. We do it for many other things using the infrastructure which you can see here. And they may take some time, but it's very, very useful. Of course, this infrastructure is not static as well. It's changing. We are adding more functionality, more new things, more new use cases. So it will also evolve over time. We'll see what directions it will go, but for now, this is what we have. Thank you very much for your time. It was a great pleasure to be here. My name is Slawomir Goryczka. I would like to thank you for having this chance to tell you about security signals, our framework to scale web security. Thank you, and I'm happy to take any questions. Yes.
I was wondering, you said that you capture about 1% of all traffic that you analyze. Is that completely random, or do you do any kind of pre-processing to try to capture interesting packets?
That's a very, very good question, because yes, we capture a little bit less than 1% usually, and it's uniformly random. But it means that for services, for endpoints which have very low traffic, we may not see them, and sometimes we want to see them, or in specific targeted use cases which we want to, for example, confirm that they have certain mitigations implemented. So there are ways to customize the sampling rate for a given service or for a given endpoint for a short period of time, and by that collect a little bit, increase the probability that we will collect the signals. Yeah. So there is some flexibility there. In most of the, maybe I can show you. In most of the components here, we have lots of knobs and settings, so you have to constantly balance them. Like we start, let's say, collecting more signals, then what is the size of our database, how many resources are used by the framework, how do we handle that? So yes, but we have this opportunity, this chance there. Thank you. Any more questions? Ideas how to improve it? Any mitigations you would like to see being rolled out? Okay. Thank you again. It was a great pleasure to have you here.